Okay, great. So, hello everyone. Let's start. And today we are discussing the attention mechanism and then the transformer architecture. So, actually, this lecture may be the most difficult, and it is really hard to fully understand transformer model, especially for the first time. But I believe, that it is possible and that you can catch everything. So let's start. In the last lecture, we have seen the make more by Andrei Karpathy on bigrams level. So we produce new names based on the data set of some current names. So we train the model to simulate these data set. Then we discussed the prior notion for more robust predictions, and then in the end of the lecture we switch to multi-layer perceptron. There we introduce new weights for training the model based on any data set we want, and again we are able to generate new text similar to the data set we used before. Okay, and today we firstly want to recover some previous models. So maybe you remember there was recurrent neural network models, and the vanilla version, so the simplest one, is then you have almost one linear layer. So based on the input of new vector xt and previous hidden state of the model ht-1, you generate, so you change the hidden state of the model and get the ht vector, and based on this vector you output new answers yt to predict a new token in the model. It may be new character or maybe part of word if you are using some other vocabulary. And here is very simple formula of one linear layer and activation function 10h to build this model, and all the orange color matrices here are the parameters of the model. So we train them during the cycle, the whole cycle. To here we solved the classification task problem. So we want to predict next character based on the previous one actually. And the disadvantages of this approach are the following. So the input and output sequence lengths must match. So we each time we see new token xt, new character, we predict another one based on yt. This is our answer. So this is one-to-one correspondence between input sequence and output sequence. Then the model reads the input only from the left to the right and doesn't look ahead. Sometimes it is not a problem, but sometimes we want to predict something based on the whole sentence. For example, if we want to solve the machine translation task and we want to translate English sentence to other language, to, I don't know, to Greek, French, or some other, then of course, firstly, we need to read the whole sentence and then translate it to another language. So for these types of problems, as machine translation, question answering, and so on, these models, recurrent neural network, is not appropriate, so we cannot use them. And how to solve it? Yeah, so the next step in modeling is so-called encoder-decoder architecture. So actually here you have two classical vanilla RNN networks, but the first one in encoder tries to remember everything. For example, again, in your English sentence, yes, or all the words in English sentence, and to encode them to one vector C. So this is the last hidden state of the encoder, HN, and it includes all the information of your input. And based on this vector C, as context, yeah, you produce new output tokens, output characters, for example, in decoder model. And the model inside decoder is the same vanilla RNN with hidden state, and each time you put one and the same vector C as input in decoder. Okay, and formulas here are pretty much the same as we've seen before. So in classical model, so both F in and F out are linear layers with activation function, for example 10H. Yeah, and this is okay, so it works. You can use this architecture for machine translation, for example, but again, here there are some difficulties too. So the disadvantages of the encoder-decoder model is that we force model to remember all the input in one vector C. It means that so the more n, the more input we have, the more difficult to pack all the information to this vector. And of course, the C as the end of encoder remembers the start of the, so remembers the end better than the start. And of course, for more layers we have, more accurate we should be with vanishing and explosions of gradient as usual. And it is actually impossible to parallelize because we need to know previous hidden state to calculate next one, both in encoder, and firstly we encode everything to get vector C, and then we go to decoder and the same logic here. So we calculate our hidden state one by one, and we need to know previous to calculate current one, and when to predict new output in our model. So these are disadvantages of RNN, and the question is how can we fix some of the problems above? So what to do to create even more suitable and better models. And the hint to these questions, again, so the intuition of improvements comes from the our people, human beings, perceiving information. So how do we perceive information? To answer these questions, it is not, of course, an easy one, but let me show you the video about basketball. So let's count the number of passes, especially if you have never seen it. So it is very useful exercise for understanding.
This is a test of selective attention. Count how many times the players wearing white pass the basketball.
Okay, yeah, players wearing white.
How many passes did you count? The correct answer is 15 passes. But did you see the gorilla? This video is from research by Daniel Simons and Christopher Chabris and is copyrighted.
So you see,
It is available for use in talks.
In the same video here, yeah, we when we focus on counting all the passes, actually we almost cannot see the gorilla. You see it here, yeah, but it is there on the video, and this is the reason of the
How many?
In our understanding. So we humans really good at focusing on some task. Yeah. So we can here, for example, focusing on counting the number of passes, and the other information is not important for us, for our brain, that we can even miss the gorillas of the big object in the video. Yeah. And that's why we want our model to have attention too. So to be able to focus on some aspects of the input, and maybe to don't put much focus, much attention to the other parts of the input. And that's why we change the encoder-decoder architecture, and we get rid of one vector of context C. Yeah? So we actually replace this vector to the attention layer. So you see here, what is the attention layer? Actually, it is some function A from two vectors, h and h prime, and the goal of this function is to count the similarity of two vectors. For example, you can use dot product, or it's the same as scalar product here, so to get one number, or you can exponent dot product to get one number, and maybe other mathematical functions, something as distance between two vectors. Yeah, so to model the similarity function. And then after, so if you have the similarity of each two vectors, of each pair of vector, then for vectors h I from the input and h prime t from the output, you can calculate the relative score, which is attention score. So how and which vectors from the input, which hidden states are important to predict current output, y1, or other current output, y2, and you will change your attention scores from moving from one state to another in the decoder, and you will change vector c1, c2 from one step to another to better predict the output. Yeah, so especially in machine translation task, if you have the English sentence and you want to translate it to Greek, then of course some words are more important for translation one part of the sentence, and then you switch to other words, yeah, and look at them for better understanding and for better results in your output. So instead of one context vector, we have a lot of them, for one vector for each step in the decoder, and we calculate them as weighted combination with attention scores. Let me show you the formulas. For example, hi is the hidden state from encoder, then ht-1 is hidden state from decoder. We calculate some similarity between them, between these pairs of vectors, for example, as dot product. Then we normalize these numbers to get alpha ti, which will sum up to 1 along the rows. Yeah, so if we add all the norm I from attention scores, then we get 1 because of the formula. Yeah, and the input for decoder, so context vector CT, is simply a weighted combination of the hidden states from the encoder with these attention score weights. So you see the formula here. And based on this vector Ct, which is different for each step t, we predict next hidden state ht prime and predict the output token or output character for this exact step in decoder. Okay, so you can of course enter, and we will do it in 2 slides. You can enter trainable parameters into your attention scores and of course into your context vector Ct, and it is even possible to refuse recurrence both in encoder and decoder. And if we do it, then we will have actually the attention mechanism inside our model. Okay, yeah, let's go on to this is the result from this white paper, Neural Machine Translation by Jointly Learning to Align and Translate. And yeah, the main types of tasks are very different: machine translation, question answering, text summarization, and so on. So a lot of different types of problems, and you can even process different sequences using the same attention mechanism and attention model. So let's discuss what is. So this is the result again from the white paper. There we visualize different attention scores, so alpha ti, for translation English sentence to the French language. Okay, and you see the articles and the words, the weights here lies on the main diagonal of these two-dimensional metrics. And this is very intuitive. So we know that agreement in English is accord in French, and so on. So, but here, the European Economic Area, we have reverse order of words, because in French it is la zone économique européenne. So we change the order of words, and the attention mechanism after training understands what is going on, so that the European is European. So the mapping between words are fully correct. Okay, and that's because of attention mechanism and our trainable weights here. So you can use attention for not only for text but for images also. This is again the example, the picture from the Show, Attend, and Tell paper. There we apply the same technique for annotating images. So your input is image, and the output is text describing the image. And for each part of the text, for example, frisbee, dog, stop sign, we can understand which part of the image influence these characters in the output. Yeah, and you see again, so the attention weights are very, very clear, because then model generates a group of people board, then it looks at the people in the board from the picture. Yeah, then we generate word trees, for example. Again, the most huge values of the attention is everywhere except the giraffe, the part of the image. Yeah, so it works. And what is inside the attention mechanism? So the most simple formula is scalar or dot product of two vectors. Yeah, so here we multiply h transposed, so the row of numbers, to the h prime, which is the column of numbers, and the dot product is simply sum of all the pair products of the components of these two vectors. Yeah. And of course we can use some other, so exponent of this dot product, and if we norm it, then it simply becomes softmax function for attention scores. And here, so the third variant, we can introduce learning parameters inside this dot product. So here we simply multiply h prime firstly on the matrix W, and then the result of this multiplication again is we perform dot product with the result, and the overall result is number depending on the learning parameters matrix W. And this is our goal. So we want to introduce more parameters to train all the attention scores to be able to catch all the connections between the input and output. So here is another variant. We simply multiply h and h prime to the different matrices of parameters. Then we add the results, perform the activation function, perform the activation, and again dot product for another vector of parameters W transposed. Okay, and now if we want to understand the classical attention, then actually, so the goal is the same. We want to calculate the similarity between two vectors, yeah? And this is the classical formula. So let's go line by line. So this is the result, attention score for hi vector from encoder and h prime t minus 1 vector from decoder. We calculate this number. And actually, we firstly multiply hi on wk, k for keys matrix. Then we multiply h from decoder, h prime, on the wq, and q is for query. So query, key, value matrices, three different weight matrices. And then we dot product results of this multiplication. Yeah, this is again transposed vector multiplied by the second result. Here is normalization, so we divided the result on the square root of d, actually to keep the variance equal to be about 1. It's not very important for the moment, but it is simply normalization of the components for the attention scores, yeah. And then we perform softmax operation for the I direction, yeah. And the scores, attention scores alpha ti, is softmax from this dot product of two vectors, yeah. And the final result, our context vector ct, is weighted sum of not of the input hidden states hi, but of the dot product of the input hidden states with new third matrix of parameters wv. V is for value. So actually, we project all the vectors to maybe one and the same space with dimension of h, or maybe different spaces, but of course we need to control the dimensions, the shapes of matrix, to be able, for example, to perform here dot product multiplication. So here the keys and queries should be in one and the same space. And the goal is to find, so based on the query from encoder, find all the keys to form the context for prediction of next character, yeah, in the decoder. And actually that's it. So the attention mechanism is a combination of these three matrices of parameters to get one number of similarity for two vectors, hi from encoder and ht prime from decoder, yeah. And that's it. So using the attention formula, Here we simply rewrite everything, so to get the same formula in one line. Okay, so we state that our context vector is the result of attention for query q, and vectors keys and values for these vectors is this formula. So we take weighted sum of all the values to get the context vector C. And this actually is a three-layer network, almost linear network again. So we have dot product inside, but the main part is three linear layers that compute a combination, a weighted combination of values relevant to the query Q. So this is attention model, and in PyTorch, for example, we can simply import these attention block to implement the attention mechanism in our model and to get the context vector C. So for the encoder-decoder architecture, the example from the previous slide, we have h prime t minus 1 from decoder multiplied by the weight matrix WQ and perform the attention formula with keys and values from the encoder state. So from encoder, actually we have all the set of vectors h1, h2, and till hn, and for each vector of decoder we calculate context vector CT by the attention mechanism. And of course, we train this model to fit all these three matrices to better predict our classification task. And the second version of the same attention mechanism is called self-attention. It is the case then both queries and keys come from one and the same space. So that's why it is called self-attention, because here all the vectors come from encoder, and the purpose of self-attention is to enrich the context between words in your sentence. For example, again, if you want to translate English sentence, you firstly need to read it so from left to right, from right to left, and this is as reading your sentence inside attention block. And then, if we understand what is one head of attention, we can perform the multi-head attention. It means that we simply copy all the attention matrices to get j different attention models, which will represent the different aspects of the input information. For example, for text, it may be parts of speech, syntax, and so on. So different heads of attention mechanism will follow different aspects of information. And the only question is how to combine all the context vectors Cj back to one context vector. Yeah? And variants of aggregating are the following. We can simply average everything. This is simple averaging. Maybe the better option, and actually this is in practice we almost always perform concatenation of the results. So we have j attention heads, and all the results simply concatenate each other to get the final context vector C. And sometimes we could even perform another one multiplication to the matrix of parameters W, but usually we simply use second variant of aggregating the output vector C. Okay, so That's it about attention model. If you have any questions, please ask, because now we will switch to transformer model. Let me show you the first formula another time. So this is the calculation of attention scores, and then the final result is context vector CT, either for encoder and decoder parts, or in self-attention only for encoder parts. So yeah, encoder part here. So self-attention is a combination of parts of one sentence in English, for example. Okay, and what is transformer model? So actually, if we use the attention, we can train the neural network without any recurrent insight at all. So we look the input of the model. Yeah, let's say that it is the sentence from words in the input language, for example, in English. Yeah, so these are our input sentences. Then, of course, we transform all the words to embeddings of input words, and x1, x2, and so on, xn are vectors. And having these vectors, we here can perform in encoder attention mechanism. So here we perform self-attention mechanism based on the set of these vectors x1, x2, xn. Yeah, and the result is new vectors z with the same amount. So for each input x, we have new contextual embedding z, and now all the new z vectors know information about all the input words. So, for example, the last vector zn can focus on the end of the input sequence, and, for example, on the first word if it is useful for prediction. Yeah, so for solving our general task. And then we put these z vectors from the encoder and through the self-attention mechanism. We put them to decoder. There actually we have embeddings of output sentence words. Yeah, and here again we perform attention block between the contextual embeddings from encoder and the embeddings of output words in decoder, and the model then generate new words from our language model. So here we don't need actually any recurrent operations. We have no hidden states inside, except embeddings of input sentences and contextual embeddings, which came from the attention mechanism. Okay, and now let's go line by line. So let's go deep into these famous pictures. So this is the scheme architecture of transformer model, and this is its first part, which is called encoder. So the encoder-decoder architecture is the same, but the transformer model use only attention inside. So first step here, you see, we get input words, for example, in English language, and we encode them to vectors x. And having these encoding vectors, we perform so-called positional encoding. So here we simply add positional encodings to our original encodings X to get HI vectors. So inside PI we have the information about the index of our word in the sentence. So for just for classical attention, the input sentence is like bag of words. There is no any order inside attention. And we want to put the index of each word into the input of attention, multi-head attention block here, and that's why we add positional encodings to our original input encodings in the model, and the result is vectors HI. Then in second stage, here you see multi-head attention block. We simply perform attention operation, and this is self-attention operation because here we have only H embeddings, so the vectors from input. So here we work only with input sentence. And the HIJ is results of attention block for vectors HI. And here also on the right side of the slide you see the standard dimensions of all the vectors. So here, for example, you see multi-head self-attention. So we have, for example, 8 heads for j's from 1 to j big, and all the dimensions of all the matrices in attention block are 64 by 512. So the 64 is the final dimension, so the dimension of result, and 512 is actually the dimension of the input. So for example, HI have the dimension of 512. Yeah, so that's why we can multiply these metrics on the vectors and get 8 different vectors Hij with 64 numbers each. Yeah. So the next step here you see add and norm, and of course after multi-head self-attention we need to perform concatenation, and the result is you see vector H prime I with the same dimension 512 as before, as the dimension of input embedding. And after concatenation we can, this is add and norm block, we can perform addition, and it is called skip connection actually. So we want to have both HI and HI prime in the middle part of the encoder and attention block. And then we perform so-called layer normalization. We will discuss it a bit later. So this is normalization of vectors, and the result is H double prime with the same dimension 512. Then we go further to this part of the scheme. So here is feed forward block, and feed forward means fully connected two-layer linear network as you see here. So we simply perform one linear layer to HI double prime, then goes activation function relu here, and then another second linear layer to get H triple prime. And this is our almost final result, yeah, because here you see another add and norm block, which is the same skip connection, so addition and layer normalization. And again, so the dimension of each output inside this transformer block is vector of 512 numbers, okay? And now this is our final result of encoder. So we have n vectors xi, and the result is n vectors zi, which are contextual embedding. So zi already know all the information about our words in English sentence and about all the connections between these words. Yeah. So the goal of this block is to enrich, to change, to share the information between different input tokens. And now, so here you see the last part of the transformer encoder is here n times, and actually it means that we need to copy this transformer model, for example, 6 times. So not 1, but 6 such blocks, yeah, performing the same operations from hi to zi, yeah. And now we are starting with zi and get z prime, and so on, so 6 times. They are connected in series, and you see here calculation can be easily parallelized because we have no any recurrent connections between our formulas. And of course we can use either pre-trained embeddings xi or some other variants. We can learn embeddings of words, and this is the layer normalization formula. And what does it mean? Yeah, what is inside these layer normalization part of the transformer model? Actually, it is not very difficult. So the S component of X after layer normalization is this vector mu S plus sigma S multiplied by this fraction, yeah. And actually, so X here is the mean of all the components, and sigma is squared standard deviation of again of components inside vector X. Okay, so we sum all the numbers from 1 to d here, and we actually change the mean and variance of the input vector X. And these two parameters, so actually mu and sigma, are vectors with dimension d. So we train them to fit means and variances to the again to solve our problem, to solve our classification task. So here the again new layer with two vectors of parameters. In attention, each time we have 3 matrices of parameters, yeah, and then here in layer normalization we add another 2 vectors of parameters. And the slide about positional encoding. So you've seen the pi, which we added to x's to get hj, yeah, j-a-h-i. And nowadays, usually we here for calculating positional encoding, we again use a very simple attention block. So it means that we want to, here you see the formula, we update, slightly change the values of x's and keys of x's after inside attention block, and we add new vectors which are trainable again, but they encode the information between the difference of I and j. It is just the information about a relative position of token x or word, yeah, xj inside the input sentence. That's why we add a little bit more parameters in our model, and again we train it end-to-end during the classification task. So it is called self-attention with relative position representations. It's not the version from the original paper, but it is maybe the most popular variant. And now we are ready to go through the second part of the transformer. Here it is, decoder. So the structure of decoder is very similar to encoder. You see on the picture, again, multi-head attention blocks and skip connections and feed forward on the top of the block. And the only difference between decoder and encoder that in decoder we need mask data from the future. So because our general task is predicting next token, next character in the word or next word in the sentences, we need to hide the ground truth answer from the model. That's why here we cut our matrix H to the first T tokens. So T vectors, yeah, HT is only first T vectors inside. And that's all the differences. When we perform again multi-head self-attention, the same as encoder, but here we work on the level of output embeddings. Yeah, so this is output words, and this is output embeddings, again HT, and the result of self-attention in decoder is again H prime T. So here is masked multi-head attention, skip connections, and actually 2 times, yeah, and then layer normalization. So the first time is we get H prime after the first time. Then after the second part we get H double prime, and here you see it is not, so the third step is not self-attention. This is the first time there we use classical multi-head attention or cross attention, because here we take the queries from decoder, these are vectors H prime, and keys and values come from encoder. You see the vectors here, this is the final result of all the encoder step, yeah, vector Z. And this is the same as vectors of context, C1, C2, and Cn, yeah, so these are vectors Z. And using them, we share information, so how to predict next token in decoder based on the tokens in encoder. Yeah, so it means that here we look at the information in our English sentence and using it want to translate, so to generate new word in French, okay, H prime. So, and next, after H double prime, we perform the same operation as in encoder, which is fully so feed-forward network, or 2 fully connected linear layers inside transformer and decoder. Yeah, and the results of these 2-layer network are vectors YT. This is our logits or raw scores using these. So there is another last linear layer on the top of the model, actually to transform the dimension of YT to the dimension of our vocabulary. So here you see softmax of the result. It means that we calculate the probabilities of next tokens. Yeah, so and the dimension of this vector of probabilities is vocabulary size. So it is all the classes in our task. For example, all the words, yeah, in our dictionary. And then goes the generation step. Here we simply, for example, either sample next word with this probability distribution, or generate next word according to the argmax of vector of probabilities, until we get the end of sequence token. This is special token, which means which says model stop here, and this is the end of generation. So that's it. This is the whole architecture of transformer model. Let's have a break for I don't know, 4 or 5 minutes. You can ask anything, and again look at this really difficult scheme, but then we go step by step. It becomes clear what is going on. Okay, great. Let's go on. And actually, we need to discuss the loss function, so the validation criteria for example, for machine translation task. And of course, so during training, we use the same loss function as we've seen before in almost all the classification task problems. So we want to predict next token, and we have the vocabulary of all the classes. So actually we want to make the probability of ground truth label the highest, yeah. And the here you see the familiar formula of cross entropy loss. So, but here you see the maximization of sum of logarithm of probability for all the tokens in the model, and if we put minus for this sum, it will be exactly cross entropy loss for classification problem, and of course we should minimize the cross entropy to better predict next token. based on our data set. So here you see even for machine translation task, we want to translate sentence S in input language, in the S tilde in output language, and here the sum goes through all the pairs and all the results, inside resulting sentence S tilde. But we sum all the logarithm for probabilities, and this is our likelihood function, or if we put minus before, it will be our loss function in the model. And actually it is cross entropy. Then, of course, we need to have some other criteria for evaluating based on samples of translation, and it is possible to do it automatically with Blur or bilingual evaluation under study, and but we cannot use Blur to train our model. Yeah, we can use it to check the result, because these criteria you see is not differentiable. We cannot calculate gradients of this step. It is discrete, and the formula is not so hard. So there is two terms: brevity penalty and n-gram overlap. And brevity penalty means the length of result. It should be, so the translation S and the reference translation S0 actually should be the same. And the first term is, you see, the fraction with length of reference sentences and the result of the model. And the second term here is product of the, again, of the let's say probabilities computed for different n-grams. So n here goes from 1 to 4. It means that the maximum is 4 grams, but we simply count which part of the, for example, bigrams from the result S comes into the reference result as 0, yeah, and then we multiply all these probabilities P1, P2, P3, P4, and you see the closer Blur to 1 actually, the better model performs according to this metric Blur. But but we use cross entropy for the training of transformer model. And let's also discuss BERT. So BERT is bidirectional encoder representation from transformers. So actually we focus only on the encoder part without decoder, and the goal is to have encoder, to have representation of words. Yeah, so actually we can train this model on any text data set we have, for example on the Wikipedia or on the whole internet and so on. So, and we have some data set with different sentences. Yeah, then we perform some embeddings, for example, with table, or embedding with transformer model, getting the X's and Z as the same contextual embeddings as we've seen in transformer model. And then we should formulate some additional task to train this part of the model. And of course, we should formulate some answers for our data set. How to formulate this task? Maybe the most popular way called MLM, or mask language modeling. So we simply mask some certain words from our text, and we ask model to predict these exact word based on the all other context. Okay, so here is S is on current sentence, then M from S is subset of mask tokens from S, so we hide them from the model and replace to the some special token. Yeah, and then we are trying we ask model to predict masked tokens on these places, and again we maximize the likelihood, or it is the same as minimization of cross entropy loss for these tasks. So we put our data set into classification task statement. And again, we train all the model, and the result for us is, of course, not the probabilities of this, but the result here are the contextual embeddings, so ZI. It is our goal, so to have a very good representation of word tokens using the transformer model. Okay, and yeah, so it is called BERT. So we only use the encoder part to get very good number representation of tokens of any nature. And yeah, so of course we can use these models and these embeddings to really different tasks. We can, for example, perform multitask learning for additional training on. So we can train our model on classification task and then perform fine-tuning on different tasks. For example, to the regression task, yeah, of prediction, some value based on the text. And if you can perform translation of your text to embeddings, so to the vectors with numbers, you can, of course, train any other machine learning models. So now your embeddings are new features for your model. I don't know, for random forest or gradient boosting or some other machine learning model. And based on these features, you solve different tasks in text space, or even in image space if you use the visual transformer model. And yeah, I here in this lecture I often say tokens instead of words, and this is true. So usually we perform training on tokens received by either byte pair encoding or sentence piece algorithm. It is not very hard, but the main goal is to have good enough vocabulary. So on the one hand, of course, we can use characters as tokens. Yes, so we can simply perform natural language processing task based on the characters level, as we've seen before. Yeah, so the vocabulary will be either 26 or 173 or something like that. Yeah, but if we want to preserve semantics of words, yeah, so on the other hand, we may want to have a dictionary with all the English words, for example. But of course, there are a huge amount of English words. I don't know, millions or hundreds of millions, and it is huge. So we cannot use actually the vocabularies, dictionaries with millions of entities inside. Yeah, so we need some sweet spot between characters and all the words, and this is the so we divide words on tokens, on popular parts, and the algorithm to do it called, for example, byte pair encoding. So starting from bytes, we perform encoding and get, for example, 50,000 of tokens overall in the whole dictionary. in the whole vocabulary. And here are actual numbers. So the first transformer has n equals 6, dimension d equals 512, and the amount of heads in multi-head attention equals 8. And the overall amount of weights inside the model was, so you see, 65 millions. Then BERT base and BERT large have already, you see, hundreds of millions weights, and then goes, and this is similar to GPT-1 and GPT-2 models. And GPT actually is so general purpose pre-trained transformer, and actually this is only decoder of transformer model. So if BERT is only encoder of transformer model, then GPT is only decoder. And for example, GPT-3 already has, you see, billions, so hundreds of billions of weights, very huge. And now, of course, there is GPT-4 and even bigger model. And again, more parameters we have, so you see here, and doubles, yes, so 6, 12, 24, and go on. So the more parameters we have, the more quality we get. It works at least up to the current moment. Yeah. And this is the final slide of our lecture. So attention models, firstly, were built into RNNs or convolutional neural networks, but now they turned out to be self-sufficient mechanism, and based on them, the transformer architecture was developed, which now actually is state of the art in natural language processing tasks. Yeah, so that's it. Thank you for your attention. And next week we will have final lecture in this term, in this semester, and we will try to implement GPT-2 variant of transformer model in code, in Python, and in PyTorch. Yeah, so I will be glad to answer your questions. Okay, great. Then good luck with your homework and all other tasks. So yeah, see you next week.
Thank you. Goodbye.